Good morning, good evening, good afternoon. Welcome to all of you to Class 9. I can't believe it's already Class 9 of DCT 302. I'm delighted you've joined us today. And you'll notice probably from my voice that I'm not completely recovered from my bronchial cold thing, whatever that was, but at least I'm thinking reasonably clearly. And so thanks to you for putting up with the unusual scheduling of the previous class, and also for the time delay of this class. The reason this class was delayed an hour, John explained in his email, is that there was a 6-hour meeting of the ACES working groups today, which I participated in by teleconference. So today we've got up-to-the-minute ACES information for you. So we'll talk about that, but I think John indicated that we would leave that for the extra half-hour tacked on to the end of the class. So let's take an hour to talk about some other stuff. I think the one big topic that we've not dived into yet in DCT 302 is video color coding, Luma and color differences, YCBCR. And for a few of you, this will be a repeat, but I think at a more detailed level of some of the concepts that were introduced in DCT 301 a year ago, which I guess is in the vault for access to some of you. So let's do Luma and color differences. And then I'd also like to kind of improvise some material today on grading systems. Honestly, it's material that I've been working on for a while. I haven't got any polished up drawings, so I'll just freehand some drawings on the screen for you. But I've been trying to work out exactly how grading systems work internally. And of course, I've known the basics for a long time, but I'm particularly interested in how the controls are mapped out and how the controls alter the data values. What's that mathematical mapping? And how does that mathematical mapping relate to the perceptual mapping? So there we are. That's what I'd like to do. So three things. It's the constant luminance Luma color differences YCBCR business. Let's say that takes around half an hour. We'll talk about grading system controls and image coding and a little bit of math. Let's say that'll take about half an hour. And then we'll do an up-to-the-minute ACES summary. That'll be the last half hour. And as usual, I'm delighted to take questions and even interruptions. Now, admittedly, some of you are hesitant at interrupting, but I do want to encourage you to do that if you wish, by voice. And as always, questions and comments by the chat transcript are also welcome. So with that, okay, sorry about that. First, I hate to use text slides and table slides, and I'll follow this up with some drawings for you, but I want to talk about the words that we use to describe perceptual attributes that are important in image coding. And it's really super complicated. So I guess, and I wish it weren't so, but it just is. So I guess the first words that we need to talk about are brightness and contrast. Now, unfortunately, those are two words that are used on the names of controls on the display devices or so-called monitors that we use. And the names on the monitors brightness, and contrast unfortunately do not correspond to the perceptual attributes. So I'm kind of at a quandary deciding where to start here. Let's start with the perceptual attribute. So brightness as a perceptual attribute relates to luminance, which is the technical term that I've been using throughout the course. Luminance, as I think I mentioned previously, comes in two flavors. It comes in the absolute flavor, where its symbol is L, and its units are nits, or candelas per meter squared. It also comes in the relative flavor, whose symbol is Y, and which has no units. It's typically in the range reference black of 0 to reference white of 1. And these quantities are linear light quantities, or what you could call radiometric. And the radiometric aspect means those quantities go up as the optical power or the photon count goes up. And that's the whole basis of scene linear coding. That's the linchpin of the ACES system. So brightness is our perceptual notion of luminance. But unfortunately, in the electronic systems that we use, whether analog or digital, it's the gain control that alters the luminance. So I've called it here video gain. And this will typically have an icon that looks like this when it's on a display device. And unfortunately, this is called contrast. So it's an unfortunate reality that we have to live with. The control that has the label contrast actually alters perceptually what you would call brightness. And this you just have to know. Now, if you're in kind of a calibrated situation in your display environment, whether you've calibrated a projector or perhaps you've even calibrated the LCD displays that you're using in a VFX facility, contrast will adjust the luminance. And I've mentioned several times that for HD work, you'll probably want to set reference luminance to 100 nits. And ideally, you will adjust the contrast control to get there. I mean, you could build that correction into a lookup table or build it into your image data, but ideally, that establishment of 100 nit reference white will be done by the display itself. Now, there's also on your display equipment a brightness control. And the brightness control typically will have an icon that looks like this. And this is already somewhat confusing because this icon looks like the sun, and that really should be talking about brightness. But really, technically, we can call this black level. And it doesn't correspond to any particular perceptual attribute. Now, it is true that if you imagine the scale from 0 at black to 1 at white, if your image data occupies the majority of that scale, then you may get a certain image appearance. If you lift the blacks, which is what will happen if you crank the brightness control, the fact that you're bringing the black level of the image information up and displaying it at a higher luminance means that you've lost contrast ratio. So this situation might have a contrast ratio of 150 to 1. This situation might just have 50 to 1. So the brightness control, or what I would prefer to call black level, is really, to some extent, degrading the contrast ratio of the image. Now, it's not necessarily improving it, because if you move the black level control too low, you're able to chop off a whole lot of image data. So you will achieve the maximum contrast ratio of the display, but you do so chopping off image data, losing all kinds of information in the dark tones. So you want to be very, very careful how you set the black level. And you can consult my orange book if you want, or you consult your local HD engineer if you like, and ask about the picture lineup generator test pattern. And this is basically a test pattern that goes at reference black and then a little bit below reference black, about 2% low, a little bit above reference black, plus 2%. And these percentage numbers are on the code scale from 0 to wherever white is. So typically for a DVI kind of situation, this would be from 0 to 255. In fact, in DVI, it's a sad fact, you can't even generate the pluged pattern in DVI because you can't generate any code levels which are below reference black. And this is one of the advantages of using the 16 to 235 scale of Studio Video, that you can generate this picture lineup generator. Now, the algorithm is, and I might have even given you this algorithm the last class, but even so, it's worth repeating. The algorithm is present this pluged signal to your display, crank the black level or the brightness control up, and when you do, you'll see that pluged area as bars like this. You'll see a gray background and a dark bar and a light bar. Your goal in setting pluged is crank the knob down, and this bar will get darker and darker. This gets darker and darker. This bar will disappear into the background. At that instant, black level is set correctly. This plus 2% bar ought to remain visible. But this is not really used to set pluged. It's just a check after the fact. So that's the story on monitor controls, brightness and contrast. And let me just fill out the story briefly with a couple of other controls. You'll find controls on an old-fashioned video display or your own TV set at home. And ideally, you will not find these controls in your computer monitor. If you find these controls on your computer monitor, don't mess with them. They can only destroy the picture, not improve it. So if you find these controls, I mean, they will be zeroed out if you force factory settings. And that's probably the safest thing to do if you find one of these things offsetting. And almost invariably, I mean, there's no legislation about this, but ordinarily you'll find those controls on some sort of slider, and you'll usually get some numerical readout, and maybe this numerical readout is 50, and you discover that the slider goes down to 0 and up to 100. Or, you know, maybe the slider is centered on 0 and it goes plus minus 32. Anything goes. There's no standardization on this. But for the color and tint controls, or they might be called hue and saturation, the safest thing to do, and almost for sure what you get at factory setting, is the middle of the control range. So generally it's safe to go figure out what's the min and max of the control range and set those controls in the middle. And ordinarily that's a pretty decent starting point for the black level control as well. Now contrast, that is set either to the peak white luminance that you're comfortable working with, not too bright, not too dark, just right, Or if you're in a facility that sets those things to absolute levels, your facility has chosen a particular luminance like 100 nits. That's what you should set contrast to. Now, as I've indicated, unfortunately, the contrast control doesn't control perceptual contrast, and the brightness control doesn't control perceptual brightness. And so all of that just ends up being a fairly big mess, and sorry about that. We just have to live with it. Okay, so that's about all that I have to say about that. And please go ahead and ask any questions you've got on that topic, if you have any. Now, one of the reasons that I'm giving you this business is this slide, as you might imagine, plays into the knobs on grading systems, because grading systems almost universally have brightness and contrast knobs, and they operate just like I've described, just more or less like they do on a piece of display equipment. So just like on the display equipment, the so-called quotes contrast knob and the so-called quotes brightness knob do not control brightness and contrast as we understand them perceptually. So that's why I'm giving you this background slide to start us up there. So Nick, I see you're asking, would increasing saturation expand the color gamut by moving out the XY coordinates? And that's an excellent question, and the answer is basically yes. So here this is the tint or saturation control that Nick is asking about. And here I've also given you the names of those controls in video processing equipment. And so in processing equipment, we would call it chroma gain. But in a consumer display, we would call it tint. And tint I consider to be a very bad word. I'd prefer saturation, which is really color saturation. And so it does sort of, let me draw it this way. It does sort of increase the chroma of colors by moving them out closer to the limit. I'll just sketch this Rec 709 limit. But of course, if you hit the limit, you'll clip, so it's dangerous. However, the tint or saturation controls, they do not operate directly in little x, little y space. Instead, they operate in the YCBCR space that's the subject of the rest of today's talk, or some portion of today's talk. So basically, we're going to talk about this hexagon, which is in, you could call it, if you like, vector scope space. So it's in CBCR space. And, you know, I'll tell you where, well, I can show you blue is here, green is here, red is here. So the tint or saturation control directly controls that. So it's basically shrinking and spreading the colors in that CBCR space, and there's kind of an indirect relationship to how that's related to little x, little y space. So what you find is, as you alter the tint control, the colors travel on curved lines in little x, little y space. They travel in straight lines centered on the origin in YCBCR space. So if you look on a vector scope, there's straight line adjustments, but if you look on a chromaticity diagram, they're not straight lines. So, Nick, I hope that answers your question. But keep in mind that there will be a limit imposed by the gamut of the display system beyond which you can't go. And at that point, if you keep on cranking tint up, you will start clipping colors. And you'll notice that the colors are getting clipped. Now, Nick, since you asked that question, it forms a good segue for me to say that the color or hue control on display equipment, like a TV set. It does control hue perceptually, and what that control does, it basically rotates your image data underneath the display's notion of red, green, and blue. So it just rotates, plus or minus some number of degrees. Typical range might be plus or minus 60 degrees. And so it's common, or at least it used to be common in the old days when your television didn't reproduce skin tone correctly. Skin tone being somewhere, let me think, 33, somewhere around this angle on a vector scope is skin tone. So it's around 120 degrees. So 30 degrees beyond the CR axis. So you could use the hue control to rotate all of the colors so that skin lined up looking like skin. And you do that because the rest of the colors are not as critical as skin tone. That gives you a notion of what those controls do. And as I say, we're going to be headed into that in more detail as we go into the Lumichroma part of today's talk. So actually, I think that's where we're headed now. So if you've got any more questions, ask away. Otherwise, I'll be changing my slides here to put up our Lumichroma slides. Okay, here we are. So we'll talk about first the rather deep conceptual issue. It's really the basis for Luma and Chroma encoding in video. And it's perceptually motivated, so it's important to talk about in terms of image appearance and perceptual effects of images, even if you're not going into video space. But it's worth spending 15 minutes talking about video space in any event. So, so we start with this diagram at the top, which is in linear light space, and it's in our familiar linear light coordinates. So let's start there. So the top portion of the diagram says basically if you start out with red, green, and blue seen linear, well, yeah, let's not worry about whether it's seen or display, but we start out with linear light components, RGB. We know that we can form a weighted sum of those components to get relative luminance, big Y. And those weights are usually something like 0.2 red, 0.7 green, and 0.1 blue. The exact numbers vary depending upon which RGB system you're in, but the bulk of luminance is in the green channel, and most of the rest is in the red channel, and a little tiny bit is in the blue channel. Why are all really colorful blues dark? Because blue has got such a small contribution to the luminance component. Why are all colorful yellows light? Because yellow is red plus blue, and that's already at 0.9 on the luminance scale. It's got to be bright. So we work out what those weighting factors are, and here I'm drawing those weighting factors as a matrix P. We'll get to the other two components in a little while. But doing a mixture of red, green, and blue to form luminance in the linear light domain requires about 11 bits. And don't worry about those two chroma channels. We'll take care of those later. But we're going to need to have 3 channels in the pipeline. We'll get to the 2 chroma channels. 11 bits, that's a bunch. We'd really like to be able to shrink that data path down to about 8 bits for commodity consumer class video. In order to do that, you've learned about the CIE L-star function, which is about a 0.4 power function. And that's highly economical because 8-bit components are really convenient. Now, at the decoding end of the system, so over here is encoding, and over here is decoding, and I don't really, I've drawn the little continuation lines here to say I don't really care what happens in the middle. Distribution, recording, anything goes. But at the other end of the system, we've got to invert that L-star-ish encoding, and 1 over 0.42 is very, very close to 2.4. So we invert with a 2.4 power function. So this is a way you could get from linear light RGB at kind of the transmitter end to linear light RGB at the receiver end, forming a compact signal related to luminance in the middle. And this is a block diagram that a color scientist would be extremely comfortable with. But problem is, it's not good for video engineering. And it's not good for the following reason. Video systems have always got displays. And displays historically, here it's the CRT, have got a 2.4, or you might call it 2.2 if you're sRGB, or you might call it 2.6 if you're digital cinema. But the displays that we're used to using have got this power function built in. Now, the functions like 2.2 or 2.4 are part of the physics of a CRT. But when LCDs came along, the LCD vendors realized, even though the LCD itself has got this kind of wacky S-curve, they realized we're going to have to make this behave like a CRT in order to replace CRTs. So they built signal processing in to make the LCD behave like it had a 2.2 or a 2.4 function. So LCDs replaced CRTs, and we still had the 2.4 function at the back end. So this scheme that the color scientist was comfortable with, transporting RGB information from an encoder to a decoder, has to be corrected by basically reversing that curve out of the CRT in order to be used in that block diagram. Now, the video engineers in the early days, long before LCDs, but they were faced with very much this sort of consideration. They knew how to do the correct thing in color science. They knew that the 2.4, 2.2 function of this CRT would force this operation to be performed in the electronics of every decoder. And they noticed, look at this. This is a 2.4 function, inverting L-star. This is a 1 over 2.4 function. Wouldn't it be a clever idea to switch the order of those operations, putting the 2.4 right next to the 1 over 2.4, making those operations disappear? And the only thing that's left in the electronics of the decoder is the dematrixing. Now, the dematrixing is going to come from those other two signals, the two chroma signals we'll get to in a moment. But wouldn't that be a nice way to build every receiver? That's what they did. So what happens, though, is because we've altered the way that the decoder works, we have to alter the way the encoder works by switching the order of operations just like we did here. So we switch those two operations at the encoder, and what we do in video is first we do gamma, then we do matrix. And the gamma is typically done in the camera of a video system. So your typical HD camera set up in HD mode does gamma correction in the camera itself. Now, the camera may deliver RGB out, but with primes on them, or the camera may also deliver YCbCr, but that's a different story that we're headed towards. But no matter which, the gamma comes first. So the key conceptual point here is that the color scientist wanted you to do matrix and then gamma. Sorry, my color doesn't show up very well, so switch my colors here. The color scientist wanted you to do matrix and then gamma, but what we decided to do is gamma and then matrix. Now, this block diagram is built into all of the video equipment you'll ever use. And so I just want to make this bridge for you between what's ideally theoretically correct by color science and what we actually do. Now, because in previous classes, I think the last 2 classes, I've been telling you about linear light 3x3 matrices, and the important part of that is that's in an ACES IDT. That matrix takes place, oops, need to switch colors again, sorry. That 3x3 matrix needs to take place in front of gamma correction. I mean, this matrix to make YCbCr is also a 3x3 matrix, but this one we call the linear matrix. And as I say, this is built into IDTs in the ACES workflow. So this matrix is happening in linear light quantities. This matrix is happening in gamma corrected quantities. And when somebody hands you a 3x3 matrix, you have to understand that it has to be used in the correct place. So this is another element of bridging from the color science diagram where, I mean, this is already a linear matrix, so your 3x3, your IDT could be in that space. But in video, it's different. So again, in video, we expect all of this business to be built in. This is built into the encoder. This is built into the decoder. So ask away any questions. That's, oh, no, I'm sorry. I have 1 or 2 more slides to go here on this section. So let's go to the next section. Now, I'm going to ask your indulgence, and I'm going to skip this slide. Honestly, because I've kind of changed the way that I describe this, and we've already heard about that story elsewhere. So now it's time to introduce the 2 other components, and they're the color difference components. And they're called CB and CR. So I'm going to add those or insert those in addition to the Y prime. Now, because we're not using the color scientist's block diagram anymore, we are not making luminance anymore. Well, relative luminance, which would have been symbolized Y. We're making a quantity related to luminance, and it's also related to CIE lightness, related to L star, but it's not either of those things exactly. So we have to give it a new symbol, and the symbol is big Y, but with a prime on it. And the name is Luma. It's just kind of related to luminance, but it's not exactly luminance. And it's a short word because the other 2 components are, whoops, misspelled. The other 2 components are chroma. There's 2 of those. Now, we came out of this gamma correction with R prime, G prime, B prime. We then do a matrix which produces 3 components. So this is just a 3x3 matrix. And in a few moments, I'm going to tell you exactly what that matrix does. But in very loose terms, what happens is it removes from the CB and CR the lightness information and leaves only pure color in the absence of lightness. And this is why we get that vector scope diagram, which has got the center axis is the grayscale axis, and the colors are around the outside. So that's an aspect of removing the lightness information from the two chroma channels. And we invert that just by applying the inverse matrix and then applying the 2.4 function, which takes place in the display. Now, the reason we go to the trouble of doing this whole piece of business up front is, well, first of all, we get to shrink this channel from 11 or 12 bits down to 8. And second, human vision has got very poor ability to perceive detail in the pure colors, but it has very good ability to discern detail in lightness, or what's related to luminance. So it turns out that if we map these RGB signals into a domain where luminance has been removed and just pure color remains, we can filter the two color components dramatically. Basically, we throw away information in the chroma channels, and human vision can't notice. Well, if we throw away huge amounts of it, we start noticing. But we can throw away a lot and not have the viewer notice. So I've diagrammed this discarding of information. This little symbol in a block is what an electrical engineer would draw for a low-pass filter, or LPF. And I'll show you in a few slides from now what sort of low-pass filters we use. But basically, there's fewer pieces of information here than there is here. In fact, the fewer pieces of information, it's what leads to this notation 422. There's less information in the chroma channels than there is in the luma channel. So details on that later. Now, I have to warn you, though, before leaving this slide, or before leaving this section, I guess I should say, that there's one downside. And the downside is that if you discard information, you slow down the rate of change of that signal. So here I'm showing you a diagram that shows luma symbolized, well, I'm sorry, true luminance symbolized in gray, and true chrominance, but with information discarded, so the rate of transition is much slower. This is what the signals look like in the electronic domain, but when you do the color science, what happens is in the optical domain, for certain color transitions, the luminance is not produced correctly at the display. And here I'm showing you a classic example of the transition from the green color bar, and I should have colored my drawing already, but I'll color it for you now, and the magenta color bar. And between those bars, there's a dip that takes place in the luminance. So the true Y, the color science Y, dips. And this is not an optical illusion. This is actually the luminance physically being reproduced incorrectly. So this is the only downside to going into a YCBCR 422 space. And there's other flavors which you'll learn about in a moment, like 420. So this departure from color science theory causes very, very, very subtle image artifacts which almost nobody notices. So in the video domain, we do it all the time, and we almost never get caught. Now, having said that, let's go and do some details. So the first thing that I want to show you is not the first slide. The first thing that I want to show you is this slide. So the conceptual notion here is that we're taking the whole screen and dividing it into, obviously, pixels. And what I'd like to do is take little 2x2 areas of the screen. So little 2x2 grids, and then I'm showing you the red components, the green components, and the blue components of that 2x2 grid. So basically, you can think of these as being overlaid on the screen, red on top of green on top of blue, but I'm parsing them out separately here. So what we're going to do is we're going to take this 12 bytes of RGB. Just for the sake of argument, we'll say for the moment these are 8-bit components. And first, we're going to transform them through a matrix into Luma and 2 chroma components. The Luma I've shown gray, because we kind of associate lightness with gray. And this is a little bluish, it's the CB component. This is a little reddish, it's the CR component. And so far, we've still got 12 bytes of information. But we've set ourselves up here to be able to discard chroma information, because all of the lightness is in one component. So there's several ways we can discard. The original historical way is just discard horizontally by a factor of 2-to-1 in CB and 2-to-1 in CR, maintaining full bandwidth of 4 in the Luma channel. This is the 422 scheme. You can go further. Oh, and in the 422 scheme, we've shrunk our information down to 8 bytes. So that's not bad for a start. But we can go further. We can shrink the blue information even further, 4-to-1 horizontally, and the red information 4-to-1 horizontally. And now, for the equivalent of each 2x2 grid, we've got one CB sample and one CR sample. This sample you can think of sort of as over here. So we've shrunk to just 6 bytes instead of 12. So here we've got 50% data reduction for free. Now, this was a very old-fashioned way to do things that mimicked VHS machines. The modern way to do sampling at the 50% level is to do one of the 2 flavors of 420 sampling. So here, basically, we take these 4 CB samples and we scrunch them into 1 byte. Take these 4 CR samples, scrunch them into 1 byte. So again, we get 6 bytes for the 2x2 grid for a 50% reduction. These are the modern ways of doing subsampling. So this one I put MPEG-2 here. This is also H.264, H.265, just very recently agreed upon, VP8, VP9. Lots of the modern video codecs use this scheme. And it comes from a human vision consideration. We can't see the chroma detail that's missing because all the lightness detail is still there. That's the fundamental scheme behind chroma subsampling. So that's the slide I wanted to show you first. And so let me go backwards in my slide deck and show you the basic transform from the RGB cube into YCBCR space, which is also a cube, but the RGB cube that we started with has been basically rotated and skewed and becomes what a geometer would call a parallel pipe bed. See if I can spell it. Parallel pipe bed, also known as a rhombohedron. So basically, we've gone to our representation where the grayscale in the original cube is now just the luma component, which is the vertical axis in this coordinate space. And the other two axes are the CR and the CB. And the advantage of doing so is we can filter in this domain as long as we maintain all the luma information. Now, there's a very interesting aspect of this mapping, which is there's whole fairly large regions here of space which are not occupied by so-called legal colors. So the RGB cube almost fills RGB space. Now here I've drawn the version of the cube that shows you studio video coding. So from 0 to 219 in 8-bit space is the scale from reference black to reference white. And really black is down at this corner and white is up at the other corner. So I've left the footroom and headroom regions that are standard for studio video. But even without the footroom and headroom regions, when you do this mapping to bring the RGB cube into YCBCR space, there's huge regions that are unused. So basically, if you go from 8-bit, 8-bit, 8-bit RGB, really you've only got 8-bit Luma and 7-bit CB and 7-bit CR. So you do lose some nuance in the color. Or another way of thinking of it, you start with 16 million colors, but the RGB cube here only occupies 4 million codes of the YCBCR space. So there is a little bit of loss in this translation, but we live with it. The mathematics to do the translation looks like this. It's just a 3x3 matrix. We've got these numbers, which are blue contributes a little bit to Luma, green contributes a whole lot, red contributes a fair bit. These weighting factors are a function of the sensitivity of human vision to the different primaries. But here I'm showing you a translation into a rather wacky, obscure space where the math works really well, but it doesn't lead to a convenient set of numbers. So all we do here is scale those numbers into CB and CR. And I'll very, very, very quickly show you the scaling equations. This is basic theoretical color space. The chroma components go to ±1. That's not convenient. So we simply scale the two chroma coordinates. That's all that's going on here. We go into either PBPR space, which is JPEG color space, actually. JPEG does all of this arithmetic because they get a 2-to-1 data compression for free. So this scheme is the front end of virtually all JPEG compressed images. So PBPR is one flavor. The other flavor, and the one that is used universally in digital real-time video, is called CBCR. And C stands for chroma, and the CB is closely related to blue, and the CR is closely related to red. What you're looking at here is the hexagon that results from projecting that parallel pipette down onto a plane. And so white and black are both located at this spot, and the whole grayscale axis is here. But pure blue is out here at an elevation of about 0.114. Pure yellow is out here, but at an elevation of about 0.886. So what you can't see from this diagram is the elevations or the levels that those colors take place in. But this is the vector scope diagram. So when you're doing color grading, when you're doing HD acquisition, you've probably got access to a vector scope. This is exactly the coordinate system that you're seeing. And, you know, if you happen to be writing code, you can use the equations. But if you're using the equations, you probably want to get yourself a copy of that orange book that talks about all of the details. So that's CBCR space. So now if I can come back to Nick's question about what happens when you rotate hue, well, what happens when you rotate hue is you just rotate your image data underneath those points. And, you know, as I mentioned before, hue rotation might have a knob that controls rotation plus minus 60 degrees. In fact, in a grading system, the hue control would have a rotation plus minus 180 degrees. They'll let you put anything anywhere. But as soon as you start rotating hue, of course, you're changing the perceptual meaning of that color. And that may be useful for stylistic or artistic purposes, but there's no technical degradation in the signal path which will ever cause hue to change. So you really don't want to be adjusting hue to try to compensate for poor picture quality. Other adjustments are more appropriate. So that's the story about the vector scope and about color difference space. Now I think I've got a nice diagram earlier that shows you this projection of the cube. So there you go. That's, if you just imagine taking this this diagram and just dropping green down here, blue down here, magenta down here, yellow goes down here, cyan goes down here, and then joining those up, that's the hexagon of the vector scope. It's as simple as that. I mean, it's not that simple. You've got a 3D coordinate system describing all of the colors in 3 coordinates, but you're looking at it on a 2D plot. But that's what's involved. That's the basics of the vector scope. And okay, and there's math, there's matrices. If you need them, go look them up in the Orange Book. Now, I was mentioning, as we're going on, the headroom and footroom business. And just like there's headroom and footroom in the studio video levels, and we've talked about R prime, G prime, B prime, across the wire, like to the connector, and here this would be, say, an HDSDI link. Across the wire, those guys like talking about black being code 16 and white being at 235 on the 8-bit coding scale. But more typically in studio video, we're using a 10-bit scale. So these are the 64 and, and 940 numbers. But those are what I call interface numbers. And in terms of doing arithmetic on those numbers, you'd really like black to be 0. So I prefer the 8-bit scale 0 to 219, or the 10-bit scale 0 to 876. So that would be R prime, G prime, B prime. That would also be Luma. So again, over here is what I'm calling the processing scale. And the reason for this is extremely simple. The reason for this is, if I want to take video numbers and just multiply them, say I want to multiply them by 0.8 because the whites are too bright, so I just want to drop that white down. Well, multiplying 16 by 0.8, that's 4/5 of 16 is going to be pretty close to 12. Well, I don't want that multiplication that's dropping and scaling everything. I don't want it to move black. That's basically a big disaster. So whenever I do these multiplication operations, I want to do those operations on a scale where black is 0. It's really pretty simple. So what you have to do is remove the interface offset before you do the math. And that's why I talk about processing scale. Now, that little piece of business is processing scale on Luma or on RGB, but there's also headroom and footroom regions in Chroma. And on the 8-bit scale, the Chroma reference points are plus minus 112. So the pure colors live there. So yellow has got a CB component of minus 112. Blue has got a CB component of plus 112. There's some headroom region to accommodate, well, let's just say different things. So you just have to keep that in mind. And some of you may have encountered image data that's so-called full range. So it's called full, it's called extended. After Effects calls it full swing. You have to know, some people who are originating, they originate data all the way from 0 to 1023. And so processing equipment that eliminates the 0, the black offset, well, it'll screw up and generate the wrong data. So you have to know when you're coming into a grading system or a DI system, or even coming into After Effects or VFX, any of those situations, you have to know whether your image source is full swing or what you could call studio, or some people call it normal, although it's hard to know what normal is anymore. Or you might also call it legal. Those are the words that you might use to describe the studio standard, where the reference black is lifted somewhat above the minimum number that you can pass across the interface. Okay, so that's a little discussion of headroom, footroom. Now I have to warn you, and this is an uncomfortable, horrible thing, it's different for HD. So there's a set of equations you use for SD. These are the equations. That's the shape of the hexagon. And there's a different set you use for HD. Here's the equation. Here's the hexagon. And you just have to know which one is which, and you have to do the right one. Now, this, in my opinion, was really stupid standards development move. I mean, I believe it was a mistake. But it's in the standard. It's what's used. We have to stick with it. So you have to know that there's SD and HD flavors of YCbCr, even though there's only one flavor of RGB. So there's two different coding systems, one for SD, one for HD. And you can tell if you glance at a vector scope because the vector scope looks different. You know, magenta's way out here on the HD instead of being kind of here for the SD. So sad but true, live and learn. You just have to put up with it. So it's what I call HDTV chaos, and I make the point that it's chaos because that standard was established when there was SD and there was HD, and HD was either 720 or 1080. Nobody ever thought about what if there's 540p. Well, this is YouTube's standard video format these days. And should we call that, should we use SD luma coefficients or HD luma coefficients? Well, it's up for grabs. Personally, I would like to use HD for everything above 480, but this is not standardized yet, and it's a problem, and we all just have to live with it for the time being. So there you go. That's the LumaChroma-Talk, and there's hardware block diagrams in the Orange Book, and don't have to worry too much about it. So, all right, that's the end of that piece of business. And I promised you then that I would talk about grading systems, and I'm going to talk about grading systems just by making some sketches on the back of a napkin, otherwise known as sketches on your screen. So, okay, and again, feel free to ask questions. Anything goes on our way through this. So basically, I wanted to tell you about grading systems, and this is, I've got about 30 pages of notes here that I'm going to turn into a new chapter of a new book, and you guys are getting it before anybody else gets it. And so it might not all hang together, but we'll certainly give it a try. So the first thing that I'd like to talk about is lift, gamma, and gain. And this is a typical presentation that you'll see on a grading system. The small knobs, and sometimes it's a ring around the trackball instead of a knob, but sometimes it's a small knob below the trackball. And this is called master. And lift is basically exactly black level, but with one exception. It's black level would normally basically move your image data to the left or right across the fixed output space. This is the best way that I've found to describe it. So in this direction, this is moving black level up. This is moving black level down. So you're taking your image data and you're shifting it back and forth. But of course, in this presentation, you're also shifting the white level because the display will have a certain capability for white, and at some point you'll clip. If you take brightness too high, you'll clip. So potentially black level introduces clipping in the whites, which we don't want. So we changed the name to lift, and we changed the algorithm slightly so that we fix the white point and shift the blacks like this. So I'm sorry, my sketch isn't perfect, but the idea is we fix the white point. Black is altered. Tones in between are altered proportionally to their distance to black. Now, typically, these adjustments will all take place in the gamma-corrected RGB domain. So I'm drawing them as straight lines, but they're not in the radiometrically linear optical power domain here. Basically, somebody did gamma up front, and somebody is going to undo it at the back end, probably at the display, with either a 2.2 or a 2.4. So these controls are operating inside the gamma-corrected domain. So this is the only difference between black level and lift, is that lift doesn't change white. So in some sense, you can think of the effect of the lift control as going like this. The lift control has no effect at white, has maximum effect at black, but it's effective all the way across the chain of the video tone scale. Okay, that's the first of the three knobs. Knob number two, well, let's talk about gain, because gamma really deserves to be the third one. So gain is going to leave black where it sits, and it's just going to either reduce or increase where your image data lies relative to the scale that's going to be output to your final medium. Now, like raising lift or black level too high, at some point the output signal is going to clip. So set gain too high, master gain too high, you'll introduce clipping. But gain doesn't do anything to the reference black point. So in a sense, gain has no effect at black, has maximum effect at white, and has proportional effect across the whole scale in between the two. Now, the third control is gamma. And what this is going to do is take your video signal level, I'll call it V, and raise it to some power, Greek symbol gamma. Now, you already know that there's gamma typically coming in, where the encoding gamma is something like 0.5, or if you talk to an HD engineer or a DIT, they may tell you, oh, I really like using 0.45, or most of my colleagues use 0.45, but I find I get punchier pictures by using 0.4. You know, you'll have discussions like that among DOPs, camera operators. You know that there's gamma on the output end of the system. It's the display gamma, maybe 2.2, maybe 2.4, maybe 2.6. This gamma applies a power function in between. And typically the gamma here, it might go as low as 0.5, but that would be a really dramatic image alteration. And it might, in other words, it might go as low as taking a square root, and it might go as high as 2.0, which is squaring the argument. But, you know, if you take, if you think of x to the power g, so if g equals 0.5, then x to the 0.5 is just another way of writing square root of x. And x squared is, of course, well, that's just x squared. The intermediate values, x to the 1 is just x. So if you set gamma to 1, it has no effect on the image data. And that's the center of that gamma control. Now, so typically you'll go gamma less than 1, which is turning that curve potentially into a square root, something like that. And maximum gamma 2.0 will turn it into a square. So that's the sort of variation you get on the gamma control. Now look what's happening here. Gamma is doing nothing to 0, and that's because 0 to any power is just 0. And gamma is doing nothing to reference white, and that's because 1 to the power gamma anything, it's just 1. So the gamma control basically has no effect at black, no effect at white, and maximum effect, well, somewhere in the middle, depending exactly what it is. So let's draw the gamma effectiveness curve sort of like that. So basically, gamma is just changing the midtones. lift is just changing the shadows, and gain is really just controlling the highlights. So that actually brings us to the other form of color correction, which has got three knobs labeled shadows, midtones, and highlights. And they operate much the same as lift, gamma, gain, but they allow you to create a set point in between these tone ranges. And the shadow control has got maximum effect down here. The effect tails off, and it has no effect here. So the shadow midtone highlight approach is sort of like lift, gamma, gain, but they allow you to tailor the curves. So the shadow curve might look like that, and the highlight curve might look like that. And these parameters are then adjustable. You can adjust the position. You maybe even can adjust the slope of the onset and effectiveness of that control. So they're much less intuitive. You get a more detailed control over the image data, but they're less intuitive. The mathematics is much less obvious. So there you go. That's the short description of color grading. And as I say, you guys are my guinea pigs on this section of the talk. That just gives you an overall notion of what happens in a grading suite, or what happens with grading controls, as you might find it, both on really high-end machines, Luster, Baselight, or on sort of mid-scale machines like Apple Color or After Effects. So Nick is asking, how would you replicate printer lights? I guess the printer lights of a traditional color timing suite. Or if I can, Nick, rephrase your question, how do printer lights map into these controls that I've shown you in this drawing? So let me show you that. And, unfortunately, I can't really erase here except to erase everything. So let's erase everything. But I left one little part out. So let me give you the little part that I left out. What I left out is I showed you lift, gamma, gain. And, I showed you that some grading systems have got the master control as a knob, but some of them have got a ring around the trackball, and you rotate that ring in one direction, and that then gives you a lift value which is applied to all of red, green, and blue. Now, what's left over here is the trackball, which has basically got two coordinates of motion, and that basically gives you control of a color difference plane that allows you to send more correction into blue or less, and more correction into red or less. I'm sorry, minus red, leaving alone green. Well, it isn't exactly green that's left alone. It's luma that's left alone. So basically, what you're able to do is take that hexagon block diagram of the vector scope, and you move the black point to be something other than the ideal black point by moving the triangle. So basically, you're taking the base of that YCBCR parallel pipe head, and you're moving the base, leaving the rest of it where it is. So you're able to introduce color to black, which typically you don't want to do, but what you might want to do is remove color from black. That's more typical. So that's the differential control. So you've got 3 degrees of freedom on lift. You've got a master gamma, or maybe it's the ring, but then you can apply different gammas to the different channels. And this will change the color of the midtones, leaving the color of white and black the same. And so you can use the gamma control to turn the shadows blue and the highlights yellow. That's a popular effect in modern movies. So, and then similarly, there's a trackball on gain, and the gain trackball is most useful for exposure correction. Now, let me give you one little piece of math here. If you think of some gain value G times V, which then eventually in the display is raised to the gamma, well, this is the same as G to the gamma times V to the gamma. In other words, the mathematics here tells you you can apply gain in the gamma corrected domain, like underneath gamma, because as I mentioned, there's encoding gamma here and decoding gamma here. You can apply gain there, or with exactly the same mathematical effect, you can apply gain in the linear light space as long as you correct the gain by that value. So exposure control in a video system, because video systems are built on power functions, exposure control can be accomplished either in the linear light domain, like at the camera, or in the video gamma corrected domain, same diff, does the same thing. Now, I had to give you that little bit of preamble before addressing Nick's question, what about printer lights? Well, let me explain the printer light scenario. So what we have in video is basically we've got gamma, we've got a power function let's say we start with T being the tristimulus scene-referred linear light, and this is again ACE's terminology. So we've got the T scale, and let's say that reference white is 1.0, although we'd really like to go way above 1.0, like maybe we'd like to go up to 10 to handle really high specular exposures. But reference or diffuse white 1.0 and a 0.18 18% gray card is there. So we take a power function, we form video is something like tristimulus to the 0.5. Then we work in the video domain, and then at the end of the process, we go out, video raised to the 2.2, or maybe it's a 2.4, maybe it's a 2.6, into linear light that we present to the viewer. So this whole video thing, it's all about power functions. And just in the last slide, I showed you some power function math. Now, in cinema, it's not like that. So let me put film in quotes, like the way we used to do it in DPX or Cineon. At the front end, we did a log. Our data values were in log space, and at the back end, we did an anti-log. So here what's going on is basically, let's call it the C for Cineon values, and you know these numbers, and many of you do. You know, those are the numbers that go from 95 to, well, they go all the way up to 1023, but 18% gray in a Cineon system corresponds to code 445. And generally nobody runs any code levels below about 95. And where white is, well, it's sort of anybody's guess. But the important thing is the data that we process, like in the digital intermediate, it's in log space. And at the back end, so what's happening at front end is Cineon code is the tristimulus, but we take the log. And at the back end, we take Cineon code and we raise some magic number to that power. So instead of V to the gamma, where this is our signal, in Cineon code, this is the signal. It's in the position of the exponent instead of being the position of the base. So mathematically, video systems are way different than film systems. But we can still do adding and multiplying. And in the case of video, we also do power. So basically what I showed you, the addition, that was lift, the power was gamma, and the multiplication, put those operators in circles, this is gain. Now in log space, the typical controls, now this, you know, I hope you're just going to sort of fall off your chair here, because the controls we use in log space, like when you set a luster or a base light into log mode, which is appropriate if you're coming in with data which has been log coded, the controls are, get this, brightness and contrast. And they're called that because this one does addition and this one does multiplication. But addition of logarithms, somebody already did log of A. And, you know, if you take log of B and you add those together, well, there's a piece of math. I hope this doesn't scare anybody off, but hey, this is 300 level, 302, so let's do it. Log of A plus log of B. So really I'm going to put parentheses around these so you make sure we do log of A, we do log of B, and then we add them. Mathematically, that is equal to the log of A times B. What that means is when you're in log space and you add, you're actually really multiplying the scene linear values, the basic values. That is exposure correction. That's the printer points. The printer points are just added. So some people call them printer points. Some people call them printer lights because originally in a film development process, they were lights. So adding the lights is equivalent to multiplication of the scene linear radiometric values. So you do exposure correction, and this is getting very colorful now, but you do exposure correction using the brightness control when you're in log grading, but you do exposure correction using the gain control when you're in video mode. And to make it even more confusing, the grading people call this linear mode. So there's two completely different ways to do grading. They got different knobs. And you know, I hope you find that useful. You know, I don't think any of you are colorists. Well, maybe. Let me know if you are. And if so, you've just learned the basic math of being a colorist. But I think this is useful to those of you who are bringing material into a VFX pipeline or having your VFX material graded. Oh, Nick, you are a colorist, so that's superb. So then you probably found this really useful, because I've never seen this written down in a coherent form anywhere. And so I'm working on this draft chapter, and as I say, you guys get to hear it first. Now, Margaret, I see you're asking, is there any perceptual advantage to using a manufacturer's LUT in the grading pipeline, or a mathematical reason to use a LUT in addition to your own artistic judgments? So there's no simple answer to that question, but I can make a few comments on it on the way by. So in the ACES pipeline, you'll probably want to be using a manufacturer's LUT at the front end. So let me use this portion of our diagram to stand for our ACES grading system. So when you come in ACES, the first thing you'll want to do is run through an IDT, and that will quite possibly be implemented as a LUT. And you'll probably want to get that from your camera vendor. Although in the short term, you might find that the grading system vendors are kind of acting as a distribution point, because all of this stuff is still sort of in flux at the moment. What you do here is pretty much art. But if you know what you're up to, like if you know you want to do exposure correction, then basically this math that I just explained to you is how to do the exposure correction. I mean, I would probably not be a good colorist. I mean, I know the math underneath it all, but there's this delicate balance that, you know, Nick, you obviously know about. You know, there's a certain amount of Darwinian survival here. If you survive being a colorist for more than a year, you know, you must have this balance between the art and the craft and the science. And Margaret, I have a suspicion that you have that balance as well. So, you know, what I would do, I would go look at a white patch that was shot in front of the scene, like a Macbeth chart, Perish the Thought, or ideally a DSC Labs chart with a white patch. And I would want to match its data values after the front stage of grading. So, you know, I would just look at those numbers. And one way to do white balancing is just white balance by the numbers. But we're doing art. It's art that rules in the end. And it may be that the white balance in a particular scene needs to depart from perfect theoretical mathematical white for very good artistic reasons. So I don't think there's any simple answer to that question. And who knows, maybe if I really work up this color correction math business, who knows, that could be DCT 310 at some point. Okay, so there you go. So now we're already 90 minutes in, so I'd better erase this slide. And if you've got sharp eyes, you've been noticed I'm taking screen caps of my slides as we go through. And let's erase that slide, and then we won't spend half an hour, but let's plan on spending 10 minutes on the Academy update. So let me fetch out the notes that I just took earlier today. Because I just finished spending, I think it was 6 hours in a bunch of Academy meetings, and there was not 6 hours worth of material there, but it was very useful. And so let's just refresh the Academy block diagram. You've got the IDT, which is taking camera device values in. It has two halves. One half is just doing whatever curve undoes the camera coding. Maybe it's log curve. So in some sense, you could call this anti-log ordinarily. And the other half is the 3x3 that goes into ACES color primaries, so wide gamut primaries. And then typically, we'll loop that through the look management transform. or look manipulation, I guess. Look modification is the right term. Modification. And this is the transform that's attached to those grading system knobs. And then we come into the reference rendering transform, which you heard about already. We're hoping for 1.0, but at the moment, let's call it a late alpha. And then we go into one or more ODTs, and actually there's one or more IDTs because we're allowed to have multiple cameras and they all come into the same ACES space. But then we've got multiple potentially ODTs, and one of them is the special RDT, which goes out to a P3 DCI projector. So that's the block diagram that you know and love. And then the rest of them are just ODTs. So we may have an ODT out to 709. I'm not writing 709 anymore alone. I'm always putting it in combination with 1886. They're both BT ITU standards. This one does the colors. This one does the gamma. They should be the same document, but they're not. And there might even be an ODT out to, say, a Dolby display, and there might even be an ODT out to a really high performance 8,000 to 1 projector. There are a couple of vendors who've been talking about laser projectors. So there could be a variety of ODTs, but as you've heard in previous stories, the RDT is the reference. It's special. Now, what was discussed today, so this is the hot news, is two things, basically. What was discussed today is what happens when you shoot with the camera, but you really want on-set monitoring of some sort. So somehow we need to take ACES-ish data and present that to an on-set monitor. And maybe it's even a 709-ish display, although you could get a P3-ish display, either a really nice high-end OLED like the Sony E250, or potentially even a DreamQuest or an AZO. The concept that's under discussion at the Academy is called ACES proxy. And this is solely for use on set. It's not for use in the DI pipeline. But the idea is we'd like to be able to have ACES class controls, and in particular, we want the option to have color decision list parameters, which are applied on set and then carried as metadata into the DI process, and that can be a starting point for look manipulation. So ACES proxy, by the sounds of it, will come in two flavors, a 10-bit flavor and a 12-bit flavor, and both of those will be capable of HDSDI transport. So both of those are integer encodings, and they're HDI real-time friendly. And there's some draft documents up about how those might be coded. And that's topic number one. And topic number two is basically something, and I don't really like the name, but we'll go with it. Topic number two is loosely called log ACES. And that's a color space which we imagine will take place more or less around the knobs of the grading system. So, we know that the look management is going from ACES to ACES. And both of those, are the same color space. They're scene referred, linear light, tri-stimulus, huge gamut, huge dynamic range. But the knobs are not going to operate properly. You just cannot do black level, gamma, gain, brightness, contrast, whatever you want to call them. You cannot do those knobs directly on ACES data. So the notion is we're going to transform into you know, I don't want you to use this term publicly, but you can sort of think of it as GUI space. It's the color space in which the adjustments are most effectively performed. And those of you who are colorists will understand the knobs feel different in different data encodings, and the knobs feel different between the video, or what they unfortunately call linear, and the log mode. So log aces basically represents going into a comfortable space to make the adjustments and then coming back out into aces space. And you know, you'll remember that OSES, whoops, misspelled. OSES is the space at the other end, which is, from a color science point of view, identical to ACES, but ACES is scene referred, and OSES is display referred at something around 48 nits of peak white. So there you go. There's the two new concepts. There's ACES proxy for use on set up very close to the camera, and log aces, which by the way will have a 16-bit integer encoding. I mean, you can also do 16-bit float or 32-bit float if you're inclined, but a number of the current color grading systems are 16-bit integers, and log aces is intended to be friendly for those implementations. So there you have it. That's up to the minute news. That's, you know, I actually had to cut away early from the meeting, which went overboard, to come and join the class, even though you very kindly delayed the class for me for an hour. So Jefferson, you're asking, the purpose of log aces is to do perceptual adjustments, and that is more or less correct. So we do want these controls to operate in a perceptual space, and log aces is somewhat perceptual. Now, I can give you the short story here. It's basically, it's a logarithmic encoding from top to bottom, having a certain number of codes per stop, and a lot of stops. It's the same number of codes per stop up and down the whole scale. And it's the belief of everyone working on it that this adjustment in that space will adequately mimic perception, which knobs directly in ACES scene linear space would clearly not. I mean, another way to think of it is, I mean, you could, I suppose, and I can't find a good place to draw this bit. Let's try drawing it up here. So you could, I suppose, do the LMT arithmetic and put lookup tables behind the knobs, if you like. So, I mean, there's, in another way of thinking of it, you could, you know, do these perceptual transformations right at the knob, and then do the arithmetic in linear light ACES space. But honestly, I think doing these manipulations in log ACES space is likely to work better. So Jefferson, your question is basically giving the correct answer. That is the way it's intended to work. So let me offer to field, even though we're running over time, let me offer to field one or two more questions, quick ones, and we can always take this up again at the beginning of next class. But if anybody else wants to pipe in. Okay, I can't tell whether anybody's typing or not. So I think I'll wrap. We've run overboard. Thank you very much for being with us today. I had a great time doing this. I really enjoyed doing the grading control business because that's stuff that I've never taught to anyone. I've been working on it here for a few months. It's first time out. So hope you liked it, and you know, you'll be seeing that show up somewhere in polished form in a year's time. So let's call that a wrap for for DCT 301 Class 9, and we'll see you all in approximately a week's time. Watch your email for the announcement of time and date. Thank you all very much for participating. See you next week.